This tutorial is about type classes and type-level functions. To motivate why we want to talk about this, let's consider what happens if we would like to implement the sum function generically, so that the same implementation code will work for a sequence of integers, for a sequence of doubles, and so on. If we try to do that, we find that it doesn't quite work. We cannot generalize the sum function like this, with a type parameter t and an argument of type sequence of t, because there's no way for us to sum or to add values of type t where t is unknown, is arbitrary unknown type. Obviously, the sum function can only work for types t that in some sense are summable. Another very similar situation happens if we wanted, for instance, to define the fmap function for functors that already define the map function. As we know, fmap is equivalent to map, so for each functor somebody defined already the map function, we would like to define fmap for all of them at once by the same generic code. But we cannot generalize fmap to arbitrary type constructors f. Here's what we would have to write. Suppose that we tried. We would have to put f as a type parameter, f being the type constructor of the functor. Now, just as an aside, in Scala this syntax is necessary if you want to put a type parameter that is itself a type constructor. And you can do that just by using this syntax. So if we tried to write fmap like this, we will have fmap with type parameters. And we cannot write this code because f in here is an arbitrary type constructor parameter. And there's no way for us to get the map function for that f. We don't even know if it exists. Just like here, there's no way for us to get the addition operation, the sum or plus or something, for the type t. And just like in that case, the fmap could work only for certain type constructors f, namely for those that are functors. So our desire to write code more generically leads us to the need to define functions whose type arguments, for example the t and f, are not just arbitrary types, but they are types that are required to have certain properties, or to belong to a certain subset of possible types. Here, for instance, it would be integer, double, long, and so on. Maybe others. String could be considered as well. And here will be the functor types, or rather, to be precise, the functor type constructors. So somehow we should require that this type parameter in the fmap implementation is not just any type, but it is belongs to a subset, a certain subset of possible types, which we also have to define somehow. So if we are able to do that, which is the whole focus of this tutorial, if we're able to do that, then we can use the known properties of these type parameters in the implementation of these functions. Also, we would like to be able to add new supported types whenever it's needed. So integer, double, maybe a library will define this property for the type t, but we want to add new ones later. So we want it to be extensible. So this is our goal. Now the first step towards solving it, and we will be solving this systematically. The first step is to realize that this is similar to the concept of partial functions, except that applied to types. Let me then look at what partial functions are. Generally, functions can be total or partial. A total function always has a result for any argument value. A partial function sometimes has no result. For some argument values it does have a result, for others it does not. An example of a total function would be an integer function taking an integer argument, returning that integer multiplied by 3. So for any input integer, you always have an output integer. An example of a partial function would be real valued square root. It has no result for negative arguments, no real valued square root for negative arguments, but it does have a result for non-negative arguments. So that's a partial function. A partial function has a domain of its definition which is smaller than all values of that type. Now, we should also consider that here we have type parameters. So what does it mean that we have a function with type parameters? It's like a function whose argument is a type. So let's consider functions both from value and from type to values and to types. And that is the most general kind of situation. So we will have this table of all possible functions. Function from value or from type, and to value and to type. So the function from value to value, or value level function, or value to value function, that's just an ordinary function like that. So it takes a value, argument of type integer, let's say, and returns a value of type integer. So that's a value to value function. A function from type to value could be visualized like this. So it has a type parameter, and the result is a value of this type. Now this type depends on the type parameter. So first you have to give it the type parameter, then it knows what type value it needs to return, and then it creates somehow that value and returns it. Now one important observation here is that these functions are the same kind, the same sort. This function has a type parameter, and then you can rewrite this in a different syntax by writing sum colon sequence t arrow t, which will be quite similar to this, just a different syntax. So just like in the example here, first you have to get the type parameter t, then you know which types you're taking in this function. So the function sum here can be considered as a function from type, from t, to value, which is a function from sequence t to t. So this is a value, which is itself a function on a function at the value level, but that's a value, right? So functions at value level are values. Sequence t to t, where t is already fixed type, this type parameter. Finally, we also have functions from type to type. For example, if we define this type, then my data is a function from type to type. So later in the code, you could say my data of string, and that would be the same as evaluating this function, substituting string instead of a, and the result would be either of int and string. And there also is a function from value to type in principle. Now, in Scala, it will be quite hard to come up with useful examples of this sort, because these are actually dependent types. So this kind of function is called a dependent type, which means that it's a type that depends on a value. And that is not very well supported in Scala, or in Haskell for that matter. So there are more advanced experimental languages like Idris or Agda that have better support for dependent types. So we will not talk about dependent types here. Our concern will be mostly this part of the table, functions from type, either from type to value or from type to type. Now consider how these functions are being evaluated. The value to value functions are evaluated at runtime. Type to value functions are evaluated at compile time, because you cannot really call these functions without specifying a type parameter. And that is evaluated at compile time. The compiler will know that you're calling this function with string here, say, instead of a. And that would be known at compile time as you write your code. One caveat here is that if you use typecasts in the code, then you could make a runtime evaluation based on types. So type to value functions can become runtime, which is a problem because it is possible to have a bug, and a bug in a type to value or type to type function. At compile time, that's okay because you will find it before you run your program. At runtime, it's not okay. You already deployed your program, it's running, and 3 months later it crashes because of some bug. That's not a good outcome at all. So we will avoid using typecasts or any kind of runtime computation with types. We want to keep all type computations at compile time. In this way, they are safe. Consider now partial functions. So these, so far, we just considered any kind of functions here, of all kinds, value to value, value to type, type to value, type to type. Consider now partial functions. So partial value to value function is something like this. It's a partial function that takes an argument. If the argument here is an option that is not empty, then it returns the value inside this option. But if the argument of this function were the empty option, which is to say the none value, then there is no case to match that. So this function cannot process that argument value. So this function, considered as a function on options, is a partial function. If you apply this to the wrong kind of argument, you get an exception at runtime. Consider now functions from type. So partial type to value function is a function that takes a type argument, and it only works for certain types, for certain types t. And if you call this function, so this is an example of this would be this function, which I will talk about it later. But basically, the idea is that it's a function that has a type parameter, it returns a value, and when you call this function with the wrong type parameter, it's an error at compile time. Otherwise, it works. So that's a partial function at type to value level. So partial type to value function is what we would like to have. We would like to have those functions. And the goal of this tutorial is to explain systematically how to create and manage partial type-to-value functions. Type classes is the mechanism for doing that. And the idea, roughly speaking, is that the type T should belong to a certain type class or a certain subset of types or a certain type domain or a certain kind of types. And then you can apply the partial type-to-value function to that type. If we are able to implement this, then these problems would be solved. We would just say, well, sum is not just a total type-to-value function, it's a partial type-to-value function that's only defined on types T that belong to the correct kind or type class, which are summable in some sense. And of course, this code won't work. It has to be done in a slightly different way, which we will find out how to do in a systematic manner. Before we do that, let's look at an example of using value level partial functions, and let's see what's the issue there. So imagine we have a situation, we have a sequence of either int boolean, and we want to find this, the elements in that sequence that are in the left part of the disjunction, having an integer, and we just want to get a sequence of those integers out of this sequence. How do we do that? Well, we just say, take the sequence, we filter those that are in the left, which is like this maybe, and then we map with this partial function. Now, after this step, the result is still of type sequence of either. So now we're applying this partial function to arguments of type either, which is unsafe. What if that were a right element? Then there would be nothing to match. Well, actually we know in this case it's okay to apply this partial function because we just filtered all of the elements to be on the left side of the disjunction, so we know it's safe. However, the types don't show that it is safe. The compile time checking can tell you maybe that there is some problem, a warning that certain cases will not be matched, but it doesn't know it's safe. And so if you refactor this code in some way, let's say you put this part in one module and this part in another module, and then different people start to modify this, and eventually this condition is changed and it has more complicated conditions, whatever features we need to implement. And finally, it's not always the left. And so the other part of the code is also changed in some way, and you get a runtime error after some refactoring some time later. The type-safe version of this code does not use filter map. Instead of filter map, you do collect. So collect is basically a safe version of filtering only those that fit into this partial function and then applying the partial function. So partial functions in Scala are a special type, and this type has a method to decide whether the partial function can apply to a given argument. And so that's what the collect is doing. And the result is safe. It is of type sequence int, and there's nothing you can refactor here to break the safety of this code. So partial functions are safe, but only in certain places where you take care to encapsulate the possible breakage. So usually we make functions total. We either add more code to handle other cases, or we use more restrictive types so that we know that this is not just an either, it's really always left. And in other cases, for instance, there are types such as non-empty list or positive number or even this. This is a subtype of option, and if you have this, then you know it's not empty. So instead of using option, you use this in a specific function, or you use non-empty list instead of just list. And if you do that, you can do a .head on a non-empty list, and it's always safe. And the safety is checked at compile time. You cannot pass here, instead of non-empty list, just arbitrary list. So that's how we handle the unsafety in partial functions for value level functions. So for type level functions, we would like to restrict the type parameters to some restrictive subset of types so that this is safe. That's our motivation then. So let's see how this can be done. Here's a first example of a partial type level function. Consider this data type. So this is a disjunction. The disjunction is parameterized by a type parameter A. It has two cases. And the one case gives you a myType constructor of int, and the other case gives you a myType constructor of string. Well, this is just an artificial example, but this could occur in some applications. Now, notice we have defined the type constructor myType constructor, as if it's defined for any parameter A, as any type A. But actually, in code, you can only ever create values either of myTC of int or of type myTC of string. You'll never be able to define any values of any other type, like myTC of boolean or myTC of anything else. Only either string or integer. There's no other case. And everything is sealed and final, and so there's no way to add any more cases. Let's see how the code looks like for this. So here's the code. If I want to pretend that I have a value of type myTC of A for arbitrary A, I cannot do that. I have to create it in some way. The only way to create it is to use case 1 or case 2. Neither one would work. So none of them type checks, actually. For example, if I did this, I immediately get an error. Now, there's no way I can do anything here. I could say boolean, no. Case 1 is myTC int. So the only thing that can work here is this. But I cannot put here A equal to int. Either I have a parameter here or not. So I can get rid of this parameter if I want to, but there's no way I can use this myTC with an arbitrary type parameter and get a value. Now, I can define types such as this one, which looks like I'm applying the type level function to int, and I get a type. So you see, I'm using this type constructor as if it were a function of types. I apply this to type int, and I get a type t1 out of that. And this works, and then I can use t1 and t2, for example, in my code, and this all compiles and works. So this is to illustrate that the type constructor, like myTC, is quite similar to a function at type level. So it's a function that takes types as argument and returns types. just that I have to say type instead of val because it's a type level function, not a value level function. Otherwise, it's very similar to a function. So that's why I keep calling this a type to type function or type to value function, because I want to think about these type constructors in a general way. I don't want to think about them in some kind of special magic fashion. These are just functions. Their arguments are types, their results are types. And now I can use my mathematical intuition about functions to reason about them. Now, here's a way to use this in code. So for example, x2 is of this type. I can match this and I get a result. So it works. Now, what if I wanted to apply this function to a different argument? So I'm applying it to a Boolean. Now, there is no way to create a value of type Boolean, but the Scala compiler doesn't know this. So in some sense, I consider this function as a function that is only defined, so it's a type-to-type function, myTC, that's only defined for int or string as type arguments. But if I write myTC of Boolean and I evaluate this, it compiles. So the compiler doesn't check that there's no way to create this value. But actually, no code would ever compile that creates this value correctly. Like this, for example. This won't compile. Now, what I can do is I can force the type like this, using this construction as instance of, which breaks type checking. It's a runtime typecast, and it's completely breaking the type checking. There's nothing the compiler will check here. The results are going to be wrong, like this is going to be wrong. I can't really use this in any useful way. In other words, it doesn't help if you break the type checking. Type checking is your friend. This is to be used only in very rare situations when the type system is not strong enough, not powerful enough to do some extremely complicated things. And in most cases, it's not necessary. So this is cheating in terms of type checking. And even this cheating, I pretend that I created a value of type T3, but actually I have not created such a value. I cannot use it in the code still. There's nothing I can do with this in code that would be compiling and working. So this motivates me to consider that the function myTC is actually a partial type function. It is meaningless to apply this function to arguments such as Boolean, the type arguments such as Boolean. It's only meaningful to apply it to arguments integer and string. So in other words, this type function has a domain, type domain, that is the set of types to which it can be applied meaningfully. And this domain contains only two types, int and string. So the compiler, as we have just seen, does not enforce this. It does not flag it immediately as an error. However, it does enforce that the values of this type only exist for the type parameter within the correct domain, or the type domain. And this type domain is defined at compile time and is what I mean by the domain of the partial type-to-type function. Just a side note here, the type constructor myTC cannot possibly be a functor, since it's not defined for all type arguments. A functor must be a total type-to-type function. Partial type-to-type functions cannot be functors. So these kind of types where you have partial type-to-type functions and case classes, they're called generalized algebraic data types, where generalized means that these types are not the type parameter A, they're just specific types. So there are some cases when they're useful. They're useful for domain modeling of certain kinds. Like, for example, you have some kind of query and the result types can be a fixed set of different result types. Then it's useful to have all these possible result types modeled directly via cases in the disjunction, like this. For domain-specific languages representing some kind of typed expressions in some way, then it's also useful. These are specific problems where people have used GADTs in a useful way. So this is our first example of a partial type function. Another way of doing this is to have a trait with code. Now, here this is just a data type. There's no code in here. So let's see how that works when you have trait with code. So that's more the object-oriented way, because it uses method overriding. So we start with a trait that has a method. The trait has a type parameter as well. And there are some case classes, so it's very similar to the previous slide, except the trait has code, has a def method inside, and the case classes override that def method. Other than that, it could be case class, just like in the previous slide. And again, you see this class extends has plus with integer type parameter, not with an arbitrary type parameter. And this extends with a string, not with arbitrary type parameter. So, just as in the previous slide, this defines a partial type-to-type function. And now this is a function that's only defined for a certain a, for a either int or string. So this code is quite similar to having defined a function plus with a type parameter a, having this type signature, except that a must be from this type domain. It's not quite the same as having defined such a function directly, because plus doesn't have a type parameter, and we can only access it by first creating a value of this type and then doing that value dot plus. So that because it's a def method, there must be this syntax, value dot plus. Another limitation is that all the functions, so you see this plus is one of the partial type to value functions. It's a type to value function which is defined only for certain types. All of these must be defined up front in the code of this trait. So if I want plus, minus, times, or divide, or whatever, I have to define all of those as def methods up front in this trait. I cannot later define further partial type to value functions here. And also, I cannot use this partial type to value function in a different one defined later. So that is quite a significant limitation. So this mechanism kind of works for implementing a partial type to value function, but it is limited. So the object-oriented way, it gives us some leverage, but it's limited. We will be using this mechanism in many cases, but we need to have a more general mechanism for implementing partial type to value functions. So what is that mechanism? To understand this mechanism, remember these values of type has plus of a here can only be of two different types, has plus of int or has plus of string. There are no other values that your code could possibly define. So let's use that fact that there are only certain values that your code can define and require these values to exist. And in this way, we will define a partial type to value function. So here's how it works. Suppose we want to define a function func with type argument a and some whatever value arguments. And we want to define this only for certain types a. First, we define a partial type to type function that is defined only for these types a. So we do it in the same way here. There's really only one way in Scala of doing this. Make a trait and make some classes that extend it with specific type parameters, like this or like that. It's the same thing. It just there's only one way of doing this in Scala. So first you create this partial type to type function which defines your type domain. It's defined only for the specific types you want. So let's call this for now is good. So is this type parameter good? And if so, then we can proceed with it. We create some specific values of these types. For all relevant types A, we create a specific value. So this would be to say we create a value of this type, create a value of this type. Just, val A equals this, val B equals that. And that's what we will do. Now, we will add an extra argument to this function func. In addition to all the arguments it already has or needs, we add another argument, which we will call the type evidence, and this argument will be of type is good of A. So this function cannot be called unless you have a value of this type. And you can only have values of this type if the type is supported by the partial type to type function. In other words, if the type is from the correct type domain that you're defining. It becomes now impossible to call this function with an unsupported type parameter A, because you will never be able to produce this value, the type evidence. Here, you can only produce values of these two types. Even if you define the type for a different type argument, you can't produce a value of that type. So you could define a type of mighty C of Boolean, but you will never be able to produce a value of that type. And calling func requires a value of that type. So, because we added an extra argument to func. So the type evidence is that value that is required now. There's a new argument that we added. And that guarantees that we will always call func of A with correct types A. Trying to call it with wrong types will fail at compile time. You can put some type evidence value for the wrong type, it won't type check. So that's a compile time guarantee. Now, you can make the trait not sealed. And here it was sealed because we were just thinking in terms of disjunctions, but this trait doesn't have to be a disjunction. It's just a type constructor. It's just a type-to-type function. And it doesn't have to be sealed. These don't have to be final case classes. They could be actually traits themselves, or they could be objects, or case objects, or they could be just classes, not case classes. It could be anything. It doesn't have to be a disjunction. We're not using this as a disjunction, really. We're using this as a partial type-to-type function. So the only thing we want to define is a type and some values of that type with specific type parameters. How we do this is implementation detail. One easy way of doing it is by using traits and classes that extend the trait. So we'll see in the sample code another way of doing this, or several other ways of doing this that might or might not be convenient in different situations. That's implementation detail. The important thing is, if we make this a trait that's not sealed, we can add new values for new types later. So in the library, say we provide this with some standard types. In an application, we want more types, so we just add more values. There's no need to modify the library code. So that's extensible. New supported types can be added in user code. And that's a great advantage. So that actually is the general solution of the problem of defining a partial type to value function. Now this solution has its cost. Here is what we have to do now. First, all calls to this function will now become calls of this kind. We have one more argument. For each call of this function, we have to put one more argument. Now this value, this evidence or type evidence, is a value that we need to create for each supported type A. So if you have 15 different types that we want to use, we need to create 15 different values. A lot of code, and that code is probably going to be very straightforward, just automatic kind of code, which software engineers call boilerplate. Boring code that still needs to be written. And finally, all these evidence values have to be passed around all the time, because you call these functions in different places in your code, have to get these type evidence values. You created these values in one place, but you have to pass them all around your code whenever they're needed. So that's a lot of extra work for if you want to use these functions many times, then in different places of your code, that would be a lot of work. In Scala, these issues can be mitigated. And the mechanism for mitigating these issues is by using implicit values, which we will look at very soon when we look at specific code. The result of using implicit values is that type evidence arguments are only explicitly mentioned at the declaration side of the function func. And when you call it, you don't write them. Also, you don't have to pass them around. They are already passed around invisibly once they are defined as implicit, these type evidence values. And also, you don't have to write a lot of code to define type evidence values for all kinds of types, because you can define rules by which new implicit values can be built up automatically from previously built up implicit values, and the compiler will do that recursively as much as necessary. So that's more or less solves all these three issues. However, I would like to emphasize that these are cosmetic issues which make code better and easier to write. They do not change the character of the code in a qualitative way. These gains will stand whether we use this or not. So we can use this mechanism, the partial type-to-type functions, also in languages that do not support implicit values. We can even use this in Java. These things are just cosmetic issues with verbosity of the code, and it's not changing the fact that we have implemented partial type-to-value functions in the most general way possible. So, what is the Scala's mechanism of implicit values? So here's how they work. You declare a value of some type as implicit. And also there are implicit def methods and implicit classes that you can define. Once you have defined it like this, you can start defining functions with implicit arguments. So like this, for example. And then once you have defined a value of this type as implicit, you can call this function by just saying f of args. You don't have to pass x into it. That would be found. So the compiler at compile time will search in the local scope for this definition, or in imports, or in companion objects, or in parent classes, and it will find a definition like this, and it will substitute that value silently and invisibly into your function. So, by the way, having more than 2 implicit values of the same type is a compile time error. So you cannot say implicit val x some type, implicit val y some type next to it. That would be a compile time error. In addition to this, Scala has a short syntax for declaring type evidence arguments, which is specifically very useful for declaring partial type to value functions. And the syntax looks like this. So it looks like you're saying that type parameter A is itself of some type. Well, it's like a type for type notation. But actually, it's completely equivalent to this code. Take all these arguments that you have and add another list of arguments, which are all implicit, and they will have automatically generated names, and the types will be this type constructor of A, this type constructor of B, and so on. So this code is just shorter, easier to read, and this is longer, but exactly the same as this. It's just rewritten. So you could have some arguments implicit written out like this, some other arguments written out like that. You can combine both. They will be all rewritten to one big list of implicit arguments at the end. So the difference between these two is that if you want to use the evidence argument in the code of the function, you need its name. And in this definition, you have the name. You define it yourself. In this definition, you don't see that name. So that name would be automatically generated. You don't see it. No matter. Not a problem. There's a special method defined in the standard library, which is called implicitly. And that method can grab the implicit argument defined for you when you define functions with this syntax. The definition of implicitly is very simple. And you could have defined it yourself. It's just defined for convenience for you in the standard library. We'll see how that works in one of the worked examples later. So these things make the code shorter. We still need to declare the trait or the type constructor as a partial type to type function. And we still need to create type evidence values and declare them as implicit. But passing them around is very simple, and calling the function is much shorter because of the implicit mechanism. So now, having done all this, let me say what type classes are. So right now we were talking about partial type to value functions and partial type to type functions. But this is not really the terminology that most people use. It is just the terminology that I find the most illuminating. It tells you exactly what we're doing. But actually, people say type class. So what's a type class? A type class is basically a set of partial type to value functions that all have the same type domain. Which means that, for example, you can have plus, minus, times, divide, let's say, and they all have the same type domain, which is numbers that can be added, subtracted, divided, and so on. So instead of saying type class, we could say some partial type to value functions that somebody has defined. That's the same thing. So in terms of specific code that needs to be written, a type class is two things. So first, it's a partial type to type function. So it's a type constructor with some code that creates specific type evidence values of specific types, T, and that defines the type domain. Second, it is the code for the desired PTVFs. So whatever functions you need to define, you write code for them, and you use that PTTF in that code to define the type domain. Also, for many important use cases, these functions must satisfy certain laws, certain equations, for mathematical reasons. Otherwise, it would be unusable, or programs will have difficult bugs. So that's what type classes are. That's a definition of a type class. Let's fix some terminology. People say that a type T belongs to the type class, my type class. What does it mean? It means that there is a PTTF, partial type to type function, called this, and this partial type to type function has a domain to which type T belongs. So, for example, integer could be T, and then integer belongs to this if that type domain includes the integer, which means that there's a type evidence value of type my type class int. So if some value of this type can be found, then the type belongs to the type class. That's what it means when people say that. Now, a function with type parameter requires for this type parameter the type class my type class. What does it mean? Well, it means that actually one of the arguments of this function, usually implicit argument, is a value of a type like this, which is constructed using a partial type to type function. So if you see that there is some partial type to type function lying around, then you know that this is a partial type to value function that requires a type class constraint, where it constrains a type parameter to belong to the type class. Otherwise, it cannot be called with that type. Now, another important terminology is that the evidence value, the type evidence value, which is this extra argument of this type, that value itself is called not only type evidence, it's also called the type class instance. Now that terminology is completely equivalent to type evidence. So I prefer evidence, but instance is also standard terminology. I will explain how to create these things in many examples now. So typically in Scala, you create a trait with a type parameter, like this. Then you create code that makes values of this type for various types T. All these values are declared as implicit, and somehow you make them available for user code, either via imports or put them into companion objects for the types T, which is quite convenient, because then you don't need any imports. Then you also write some functions that have implicit arguments of this type. Usually these methods are def methods. These functions are def methods in this trait. They don't have to be, but often they are, because that's sometimes necessary and often convenient. So as a rule, a type evidence value should carry all the information they need about the type T. We'll see why. Let's look at examples. So Semigroup is a type class that actually, let me show you what it is. A type class that has an associative binary operation. So, in other words, there must be this function, which is a partial type to value function, that takes two arguments of type T and returns a value of type T. So it's any kind of combine operation. So combine two elements and get another element of the same type. Combine two values in any way as whatsoever, as long as it's associative. So it doesn't have to be commutative, doesn't have to be any inverse operation to this. Just can combine two values into one larger value in some way. Doesn't even have to be larger value. We don't know anything about how it works. So that's Semigroup. It's a very weak, very bare bones kind of operation, binary operation. It just is associative. That's the only thing we know. So let's implement that operation as a partial type to value function. First step is to implement PTTF. So let's just do that. Semigroup with parameter T. Then we have two case objects that say, well, we have semigroup int, semigroup string. That's all, nothing else. Fine, so that actually defines PTTF. That defines a type constructor of which you can only have values semigroup of int and semigroup of string. So that's sufficient in principle to create our partial type to value function. So let's see how we can do this. So we can define op, which has a type parameter t. It has an x and y as required. It returns a t as required. It also has an implicit argument, which is the type evidence of type semigroup t. So now, this is it. This is the partial type to value function. You could not call this function with a type parameter t for which you cannot have a value of semigroup t. So you could not call this with type parameter t other than int and string. So this test, for example, says you can combine ints, you can combine strings, but option of int cannot be combined. This doesn't even compile because the type option int is not within the type domain of this partial type function, and so you cannot have any type evidence for it, and so it just won't compile. So that's great. Now, how do we implement this function? Well, we have to add somehow integers or strings, but how do we know which is which? So let's see. This evidence is the argument, so the only thing we know about the type t is this evidence value. So we can match on it. There are two cases. So it could be an int or it could be a string evidence. So if it's an int evidence, we know that t is actually int. So, well, what can we do? Well, the only thing we can do is to force x to be of int, y to be of int, add them together, and then force the result to be again of t, because we're supposed to return t. And that's what we have to do. And we can do the same for string. And actually this code works, as the test shows. The test passes. It's a very unsafe code. It's not great, not great at all. because of these as instance of operations, which are unsafe, and maintaining this code is very hard, and so don't do that. We will never do this. I'm just showing you an example of how we could do it in some way. And that actually is an implementation of a type class. So Semigroup is a type class. Op is a type class. Is a partial type to value function with a type domain that we defined, and it works for that type domain. That's the type class, the Semigroup. We have implemented Semigroup. Very ugly, but we'll do it much better in just a few minutes. This is our very first example. Note we derived the requirements for this completely systematically. There's no guessing. So we must have a type domain, we must have a type function, type constructor, and we must have the implicit evidence argument. Well, implicit is just convenience, so we don't have to write this argument here. In principle, we could. So the op function, if you look at it, it has the second group of arguments, which is this one, the evidence. And we could put this evidence here in parentheses, for example, semigroup int evidence. It's exactly the same. So this is how the function actually must be called, and the compiler writes that for us. We don't have to write that in our code. So that just makes our code shorter. Other than that, that's what's going on in this. All right, now, why is it that we had all this trouble? It's because we have no idea what t is. We know that it's either int or string. So in this case, it is int. In this case, it's string. But we don't have any functions that help us to work with that. So the way to solve this is to put more information into the evidence. So right now here, evidence is just an empty object. It has no information except the type. If we put more information into the evidence, we can get it out and work on these x and y's. So why don't we just put the implementation into the evidence instead of putting it here and having all this trouble with typecasting? So that's what we do next. We again implement semigroup, again for int and string. Now, the partial type-to-type function, in our case, is not going to be a sealed trait. It's just going to be a type function, which we define, and it's going to carry this data. So actually, you see, what we need is to combine these two elements, and that's very natural to put that information directly onto the type constructor. So now it's very easy for us to define the evidence values. So we just say this function, which is adding two integers, has this type, and that's correct. This function has this type, that's correct. So we have defined values of type semigroup int semigroup string. So that, together with the type function, defines a partial type-to-type function. So now semigroup int and semigroup string are defined, and others are not defined. We put them as implicits. Now we define the partial type-to-value function. Let's say we define a sum. That's what we wanted. There's a sequence of values t, and there's a default value for empty sequences, say. Then there is an implicit type evidence argument. So now the implementation is actually very easy. we just do a fold left with the default element as the initial value. And the fold has a function argument, which is this op. And evidence has exactly the right type. It is the op. So we just put it in there, and we're done. No typecasting, completely type-safe implementation. And yet this is a partial type-to-value function, because it can only be called on integer and string. And this is a test that shows how it works. So this is a minimum implementation, a very, very bare bones implementation of a type class, which is the sum. A semigroup is the type-to-type function, and sum is the type-to-value function. We can define further type-to-value functions if we want to, using this type-to-type function. So that's a second attempt at defining a type class. And the code is very easy, as you see. Now let's try to use traits instead. Now this is a third implementation of Semigroup. We put this method, which used to be here, we put it as a def method on the trait. So we override this then in the two specific implementations for integer and string evidence. So that defines our PTTF. And just as in the previous example, all the data that's necessary for implementing what we want is carried by values of this type. So all the data is carried by values of this trait. Now we do implicit case object, just so that we don't have to write more implicit vals. In principle, what we could do is we could say, for example, here is case object, not implicit, and then implicit val abc equals semigroup int evidence. We could do this just as well. It's just shorter to write implicit case object right here. So we have defined the PTTF. Now we define a PTVF, which is adding of three numbers, let's say. And we define it in the same way. So we have arguments at it once, and then additionally an implicit evidence argument. And then we use the evidence.op to perform the computation. Now we see evidence.op is this op that has been defined in the trait. And since it's a def method on the trait, we have to use it in the syntax, ev.op. Whereas here we didn't. So here we could define add3. We do that. You see, we can define new PTVF very easily. So this must be of type semigroup T. So how do we do that? We do ev. Ev is a function, right? So the type is this function. So we just do ev of x, ev of yz, for example. We're done. So we can define any number of PTVFs externally in user code, just like what we wanted. So that's exactly how we expect this to work. And here, instead of saying just ev, we do ev.op every time, because here op is a def method in a trait. Same things should work. All right, so So as we have seen, it is quite useful if the type evidence value carries all the information that the PTVFs need to know about the type T. And in many cases, the trait contains these PTVFs directly. In some simple cases, it can be a data type, not a trait. But actually, as we will see, the trait with def methods is necessary if we need higher order type functions. It's convenient. It's not particularly inconvenient to have it. It's just more writing to do trait with def methods. If you can avoid it, you don't have to do it. And as we just have seen, additional partial type-to-value functions using the same unchanged type-to-type function can be added later. So no need to modify the code of this trait if we want to add new partial type-to-value functions without changing the type domain. So like add3 is an example. We don't change the type domain. Sum and add3 are defined for the same type domain, for things that can be added. No need to modify the code of library if we want to add more partial type-to-value functions with the same type domain. And as we'll see later, we can combine this with other partial type functions that we define in the other code. So that's exactly what we wanted. Let's look at some more examples of type classes. Semigroup we just saw. Now another interesting type class is pointed. It's a very simple type class. It just has a function point that returns a value of that type. So that means somehow there is a special and naturally selected value of that type, and the function gives you that value. Examples would be 0, integer type, or empty string. So these are naturally selected values of the type. Or for a function type, it would be the identity function for this function type. That's also naturally selected value. So, I mean, it's not selected in the sense that somebody selected it. It's just that it's natural to consider that value. It's useful to have some kind of value of this sort. And maybe it will have interesting properties. And so if you have a value like this, then the type is pointed. An example of a type that's not pointed is a function from A to B. There's no way to have some kind of natural function from A to B. But from A to A, there is the identity function. Another important type class is monoid. Now, monoid is a type class that represents data aggregation. So data aggregation means you have some aggregator that is initially empty, and you put data into it, and it combines everything you put it into some aggregate value. So it has two functions, empty and combine. So empty is just like the point, it just gives you a value of that type. And combine is just like the semigroup, takes two values of the type and returns one. Additionally, though, we require that combine is associative, just like in a semigroup, and this law must hold. So the empty value combined with anything, either to the left or to the right, should again return the same anything that you passed in. So combining empty with x does not change x. That is a requirement. So the value of the empty aggregate is special in this sense that you can combine empty aggregate with data and that doesn't change that data. So monoids are used a lot in different contexts. So one obvious context is log aggregation. So you add logs and it's still a log. So you can add more, put two logs together. It's a bigger log, but it's still a log. So that's, you have an empty log, or you can combine two logs that are maybe empty or not, and you still have a big log as a result. So logging is one application of this, and there are other applications, many other applications. So Monoid is a very useful abstraction. So now we'll see examples of how to implement the Monoid type class by either just doing it from scratch, so implementing the PTTF and so on, or in a very interesting way, if we assume pointed and semigroup first. So pointed type class has this point function, semigroup has the op function, and Monoid has these two functions of the same types. While the names of the functions are completely immaterial, of course, you can rename all you want. The types are important. So types are the same. And so Monoid is basically semigroup combined with pointed. And we can write code exactly saying that and save us the trouble of implementing everything from scratch. So now we'll see how that works. So first, let's implement Monoid from scratch. We will not use traits, we'll not use any names, just do a bare bones implementation. So the idea of implementation is that first we do a partial type-to-type functions. So we define a type function, and the value of this type should carry all the information we need to know. And this information consists of two pieces. First, the empty value. Remember the specification of Monoid. We need an empty value and we need a combine. So empty value is just t, and combine is a function from t and t to t. So let's put these two values in a tuple. So we have a tuple of t and a function from t and t to t. That's good enough. We don't really need any names or traits or anything. We just need the data. The fact that they're called empty or combine, this fact is immaterial. This is not important. We can rename this. We can call this 0 instead of empty. We can call this append instead of combine, or add, or whatever, or op. It doesn't really matter. What matters is the types. So let's define the type domain for this partial type function. That means we define implicit values of type monoid int and monoid string. So we define these values. These are the tuples having the selected int value and the function that combines integers, and the selected string value and the function that combines strings. Let's do it this way. Done. So now we have the partial type-to-type function defined. Now let's define the function sum. Well, we have finished defining the monoid type class. Let's define some partial functions. So the function sum will take an argument of sequence of t, and t will be constrained to have a monoid instance, so, or to have an evidence of belonging to the monoid type class. So how do we do the implementation? Well, we fold on the sequence. The first argument of the fold is the initial value, which is the first element of the tuple. The second argument of the fold is the combining function, which is the second element of the tuple. That's it, we're done. So sum is implemented and it works. Let's implement the Monoid type class in a slightly more verbose manner, which might be not bad because it documents what we're doing. It also helps read the code later, because this code looks a bit cryptic. It's t, 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 parentheses. It's a bit cryptic. So let's define names. So instead of just using a tuple, let's use named tuple. Named tuple is a case class. So let's use a case class. Call it monoid. Put names empty, combine. So exactly the same type. And we define the type function in exactly the same way, except it now has names. And these names help us document what we're doing. Exactly the same definition of the type domain, except with a name. Exactly the same definition of the function sum, except now we have f.empty and f.combine, because the type class has names. If you compare with the previous definition, that was f._1, f._2. So evidence now is a case class, and we can use nice names. That's exactly the same code. Now, good. Let's look at defining the pointed and the semigroup in the same way. So we define it as case classes with, so this is the partial type-to-type function with its domain. This is another partial type-to-type function with its domain. Now this is the partial type-to-type function we want to define, and we want to automatically derive. We don't want to repeat implicit val here. How do we do that? We use this implicit def. So implicit def is a Scala feature, which is that this function will be called by the compiler whenever necessary. If it needs to produce an implicit value of this type, it will see if it can call this function and if implicit value of these types are available. If so, it will insert the code to call this function and create this value and put that into your implicit argument. All of this will be happening silently and invisibly. So we define the instance as a function with two implicit arguments, which returns the type evidence. So it takes type evidence for semigroup and type evidence for pointed, and returns type evidence for monoid. Well, how do we do that? Well, the type evidence for monoid is a value of this type, so we need to just create a case class value of this, of this type. So we just say monoid, which creates a case class value, and we need to provide it with two values, with the empty, and that is the point from the pointed evidence, and the combine function, which is the op from the semigroup evidence. That's it. So we have defined the monoid instance. The test will show that it works. So we have not defined two different monoid instances for int and string. Nevertheless, we can use int and string in our code, because this implicit def will generate them. So imagine here we had 15 different types. It's a big savings in code that we can automatically derive class instances, type class instances, from previously defined evidence values. Now, one other thing I'd like to show is that all these things are actually already defined in a library called GADTs, and also in another library called Scala. So all these type classes are pretty standard, the semigroup, the monoid, and so on. And they're defined in these libraries. And the difference between these libraries may be names. The types are the same, they're standard mathematical structures, but the names might be different. So in the GADTs library, the names are empty and combined. In the Scala Z library, there are different names, but the types are the same. So how do we use the library to define a monoid? So here's a test. So we want to say that if we have a semigroup and we have a pointed, we want to define a GADTs monoid instance. So then we do it like this. We define a value of type GADTs monoid, and that's a class. So we do a new, and then we override the functions empty and combine. Now, unlike what we did here, the GADTs library does not use case classes. It uses traits and def methods. So it means we need to override things. But that's how it is. Otherwise, it's exactly the same thing. And then we can define sum for the GADTs monoid, and we can do the same test as before. Now, one another thing that is interesting is that we can check laws in a generic way. So I implemented this function, check GADTs monoid laws, which is a function with a type parameter that takes an evidence that M is from the GADTs monoid type class. So these things are necessary for law checking. All these assertions and arbitrary, these are property checks library. Notice I'm combining all kinds of syntax here. I have type class syntax like this. I have implicit argument of another type class like this. It's completely up to me. And so this function will check the left and right identity laws that combine of empty and M is equal to M, combine of M and empty is equal to M. Now the function data is equal is a general way of comparing two elements of type M, which might be non-trivial if M are function types. So that's why I have this data is equal. By default, this is just a comparison, but it could be different for function types. We'll see examples for this. Associativity law also needs to be checked. So for all ABC, then combine A, combine BC is equal to combine ABC. So that's associativity. And then I can call this function for int, for string, but that won't compile, because we didn't define a monoid instance for double. As an aside, here's how we can check laws for the partial type to value functions in a type class. I'm using the Scala check library, and the type classes it uses itself, for instance, are the arbitrary type class. That type class means that the type has a function that produces arbitrary values of it, or some set of values. And that allows me to write for all function that, of course, cannot check all possible values, but it checks a large number of them. So then I write a function like this, which is a generic function taking any type t, as long as this type has an arbitrary instance and also a semigroup instance. And then I'm imposing the condition that for all x, y, and z of type T, the operation is associative. So the operation of x with yz gives me the same result as first combining x and y and then combining that result with z. Now, you see, I could have rewritten this function in a different way, in a different syntax, like this. I can combine the type class annotations, and this is just a different syntax, and then I don't need to write this. However, now I need to replace this with something. I need to access this operation, which is the partial type to value function in the semigroup type class. Previously, I had an implicit argument with name semigroup ev. Now the name is hidden. I don't know what that name is. So instead of doing this, I just say implicitly semigroup T. That's exactly the same thing. So implicitly fetches the value of the implicit parameter of the given type, and there's only one because there's a compile time error if there are two different implicit values of the same type. So that's how I would write the code if I didn't want to put an explicit argument. But actually it's exactly the same function definition. If I look at this function here, I use it in exactly the same way. I don't call it with any arguments. So this is just syntax. I can use this syntax or I can use the syntax I had before. So once I have defined this function, I call it by substituting different type parameters. And this itself is also a partial type to value function that takes a type parameter and returns an assertion value. And that better be success. If it's a failure, the test would fail. So that's the way I can use the Scala check library to test laws. Similarly, I have a function that tests the monoid laws. It takes a monoid evidence and then tells me that there is a combine with empty, which returns me the same value. So notice this function is defined separately from the type class, but it uses the same type domain as a type class. It does not change the monoid or arbitrary type domains. So I can combine two different type domains. So there's no problem in defining partial type to value functions later in the code without changing the code of monoid type class. Later I can define further partial type to value functions like this one, which will work on any type belonging to the relevant type class. So that's the kind of extensibility we wanted. And I use that to make my tests that verify that my defined instances for the monoid of integer and monoid of string satisfy the correct mathematical laws. Here's an example when this does not happen, does not satisfy the laws. I create an instance of semigroup for Boolean, but I use the operation which is the Boolean implication, if x then y. Now this operation is not associative. If I define this as my semigroup evidence, which is the same as to say, if I define this as my type class instance for Boolean of semigroup type class, then my law will not be satisfied. So the associativity law is not going to be satisfied. When I call this function, this test will fail, and it will print a counterexample. Let me run this actually. The Scala check library is such that it doesn't just check the laws for a large number of values of the parameters, but if it finds some values that do not satisfy the law, it tells me what those values are. It will print the counterexample values. And then I can write a test, or I can debug to see if this was a bug, to see why it did not satisfy the law, or I can write a test that will correctly pass the law. So let me just wait until this compiles. There's a number of things that it needs to do. And when this test runs, yeah, so it fails. It says true did not equal false occurred when past generated values false, false, false. So it prints a counterexample. In the previous run, I had a different counterexample, which is false, true, false. But false, false, false apparently is also a counterexample. So then I have a test here that verifies that the laws are not holding. And I use again this implicitly, just to fetch this. But I could just, instead of this, since I know what that evidence is, I could just say the bad semigroup evidence. It's exactly the same thing as to say, I declared it as implicit. So fetching the implicit of this type is the same as just using that value of that type. Alright, so now tests pass. So let me undo my change. Alright. So now let's consider a different example of type class, which is a type class for a type constructor. The example is that of a functor. So the type constructor is a functor if it has a map operation, equivalently an F map, that satisfies the functor laws, which are the identity law and the composition law. Now, we would like to write a generic function that tests the functor laws. So this function would look like this. It will take the type constructor as well as three types, say ABC, as type parameters. And it will then run the tests with various values and check that all the laws hold for this type constructor. But this generic function should require that the type constructor f be a functor. And we need to also access the function map that is defined for the given type constructor f. So therefore we say that the map must be a type class. So it is a partial type to value function whose type domain is only the functor type constructors, all the functors f that we have declared. And then we constrain f to belong to that type class in this function, in the check functor laws. We do this in exactly the same way as before. The only difference is that the type constructor now is of a different kind, is a type parameter f is a type constructor and not just a type, basic type. Nevertheless, we just declare a partial type-to-type function called Functor, which will be called like this. Its type parameter is this f, which is this type constructor, and this will be well defined only for type constructors f for which we have defined the Functor instance. In other words, we will define this implicit evidence value for each Functor instance, and we will then require that this implicit argument be one of the arguments of the check Functor laws function. We'll see the implementation in a second, and for now just know that Functor is a higher order type-to-type function. It's a function whose argument, it's a type function, but its argument is itself a type function, because f itself is a type function. So just as we do with ordinary functions, and we say that a function whose argument is itself a function is a higher order function. So here we just say this is a higher order type function because its argument is a type function. It's already. Let's look at the test code then. So we proceed in exactly the same way if you want to implement the Functor type class. It's no matter that it's a higher order type function. We do exactly the same thing. We define a trait, let's say, with a type parameter, which is this f, and we need to use this syntax with square brackets and underscore to show that this type is itself a type function. So this type parameter is itself a type function. The trait has this def method, which has itself two further type parameters because the Functor's map function has these type parameters. Now, having these two type parameters pretty much forces us to use the trait with the def method for implementing the partial type-to-type function. We could not do this within a data type because in Scala, data values cannot have it themselves type parameters. Only def methods can have type parameters. There are some ways of circumventing this limitation, but they do not significantly change this fact. They're just hiding the fact that somewhere there is a def method with type parameters. So let's not try to hide this fact, but use the trait with def methods when necessary. So this is a partial type-to-type function. What is its type domain? What are the type constructors for which we can have some values of type Functor of f? Well, let's say data1 is one such type constructor, so let's define some type constructor like this, a simple one. And let's define the evidence that this type constructor belongs to the type domain of this type function. So the evidence means that we create a value of type Functor of data1. And this value could be anything. It could be a val, could be an object. So one way to write it is to say implicit object. Another way would be to say implicit val, and then to say new here. It's another different way of doing the same thing. Which one is better is not so clear right now. Let's just use one of them. Now, in this value, when we extend this trait with a specific value of the type parameter, we need to override this def method, because this def method has a different implementation for each type, for each type constructor here. So we need to override it. So here we just write the implementation of the f map for the data1 constructor. So we already know how to do these things, and I will not dwell on how to implement the functor instance for case class. Now, this is this is the entire definition of the partial function for type to type. Now let's define our type to value function, the map. We'll use the f map, we'll define generically the map. So how do we do that? Well, the f is one type parameter, and we say this must be of functor type class. And a and b are two other type parameters. And we define the f map as the functor's f map. So we fetch the implicit value, which is this value. We take the f map of it, which is this def method, apply this to f, we get f of a to f of b, and then apply this function to fa. This gives us a value of f of b, and that's the map method. So the map method basically, by hand, we just use the f map and call it first on f and then on data1 of a. But you see, this implementation is generic for all functors. It is not specific to data1. So in this way, we have defined a generic partial type to value function where the type constructor is constrained to be a functor. This is exactly what we wanted. It would be impossible to call this with a type parameter that is not a functor, because there is the implicit requirement, so a required implicit argument that wouldn't be available otherwise. So let's see how to use this. So, okay, so we have this map function. How do we use it? Let's create some data of this type, and we just call that function on that data. It's just an ordinary function. The fact that this is a partial function is transparent. We don't have to say what the type is. The types are inferred. Data has a specific type, data1 of int. This is a specific function from int to string. So we transform this and we get data1 with values 1abc, 2abc, according to this transformation. The result is of type data1 of string. So that's the typical result of applying a functor to data. So as you see, using the function map is no different from using a non-generic function, but the definition of map is a generic one. It would not have to be extended if we have more data types, like data2, let's say, with another functor instance. Won't have to extend this function. So this is very good for library design, because we can put these functions into the library and we'll never have to extend them. It's only the user's code that needs to extend this and needs to declare functor instances for new data types, but this has to be done once together with each data type, and you're done. Here's a function that can check functor laws. It's a bit involved because Functor laws involve arbitrary functions from A to B and from B to C, and so I explicitly write down all the arguments that I need. So these are the implicit arguments of this function. Functor f is a type class for functor. Then there are these arbitrary instances of type class. So the Scala check library needs to use arbitrary values of these types to run the checks. And if I don't put them here, it doesn't know that they exist. But finally, when I use this function, I just give it some specific types, and I don't have to specify anything more than that. All these arbitrary instances are implicit values that are defined in the library, and I don't need to talk about them in my code. So for library design, this is great. The library becomes much more powerful, and no user code needs to be written. So just to be sure this is clear what this is doing, it's checking the functor laws for specific types. So data1 is a functor, and for example, a, the type parameter a here is int. So here the identity law will be only checked for the int type, so that int to int identity on data1 instances of type data1 int are preserved after fmap. That's the only thing it will check. Now I can obviously add some more checking here with different types. With other types. It's up to me. I can do this, or I can neglect doing this. But no necessary extra code. So let us see how the same works with the cats library. Now the cats library has a standard functor type class, which is the cats.functor. It works in a very similar way, except that it uses map rather than fmap. So the order of arguments is that first there's the data, or the functor, and then there's a function. Whereas the fmap has the opposite order, first the function and then the data. Now, the convention that I follow is that the implicit values should be in the companion object of the data type. Now, this is a useful convention because Scala has a mechanism for searching for implicit values, and it will search in the companion objects of the types you're using. So if there is some function that tries to find implicit value of functor of data1, the compiler will automatically search in the companion objects of functor and in the companion object of data1. Now it makes sense to put data1 specific stuff in the companion object of data1 and functor specific stuff into a companion object of functor. The functor is in the library, data1 is my own code. So that's why I first define my data1 as my own custom type, and then I define its companion object, which is in Scala just an object with the same name as the type. It's a special convention in Scala. So in this object I have my implicit value. I can do implicit val and then equals new if I want, or I can do implicit object extends this. It's up to me. There is not a big difference and not a very different amount of code to be written. Then I write the implementation of the functor instance, So I implement the map, and then I check the functor laws. So this function is very similar to what we saw above, except it uses the cat's functor type class with the map in it. So that's implemented in my test code. Very similar code that checks the identity law and the composition law, given 3 arbitrary types and a type constructor that must be a functor. So now, having seen this, let us take an overview of what we have achieved. We have been working with type-to-value functions and type-to-type functions. Let's compare value-to-value functions and type-to-value functions. Now, value-to-value functions is the ones that are the ordinary functions. The domain of a value-to-value function is the set of its admissible argument values. We call that a type. So a type is the subset of values that are admissible as an argument of function. So for example, if the function takes an integer type of the argument, then strings are not admissible, arrays of something are not admissible, nothing else except integers are admissible. So in the set of all integer values is the value domain of that function. And that's what we call a type. So the function can be applied safely only if the argument is of the correct type. And this is the example of having a function. We declare its type, and then we apply to some y value. And unless y has this type, this is not safe to do so, so not safe to apply. And if y is not of this type, there will be a compile time error. That's how we use types. Types prevent applying functions to incorrect arguments. Now let's look at a partial type-to-value function. It has a type domain, which is the set of admissible argument types or type parameters. The type domain is a subset of types, a subset of type parameters that the function can accept. So that is actually called a kind. This is terminology that is accepted in functional programming. So we say that the type-to-value function can be applied only to type arguments of the right kind. Similarly to a value-to-value function that can be only applied safely if the argument values are of the right type, a function like this, where we declare its type parameter constrained to be in some type class, this can be safely applied to a type parameter A only if A belongs to this type class. We say only if A is of the right kind. And in both cases, the error will be caught at the compile time. So if this is not the right type, if this type does not belong to this type class, writing this code will not compile. In the case of PTVFs, that will happen because the implicit argument will not be found. But no matter, it will still be a compile time error. So kinds are the type system for types. Values are of the right type, type arguments are of the right kind. So a type class, such as my type class, defines a new kind as a subset of types. And there's a type notation that we use, and there's also a kind notation. Now the kind notation is not part of the Scala language, but we need a notation nevertheless to talk about kinds. So I suggest to use this notation. So star is a standard kind notation for any type, basic type, like integer or string, an actual type that has values. So star is a type that has values, any type that has values, and if I denote it like this with a type class annotation, that means I'm only considering types that belong to the type class. Another existing available kind is a type function kind. Notation for that is this. So let's look at an example. Consider this type. In here, f and t are types of different kinds. F is a type constructor, t is a type, basic type, not a type constructor. So f is a type constructor or type function, and so f has this kind, is a function kind, which is similar to a function type except for types. So it takes a type and returns a type. The kind of t is the star. T is just a basic type. The kind of f is the function from basic type to basic type. So this is the kind notation. Star means the basic type, arrow means a function, and colon with type class, I suggest to use that for type classes. Here's an example. We can define a type like this. This is a type. This is also a type, but this is a type function. This is also a type function. So the kind of this is actually this expression. It has two arguments. The first argument is a type function, which is this kind. The second argument is a basic type, which is a star kind. And the return of this type function is a basic type, which is a star kind. The return is a basic type, pretty much always. And so that would be the kind notation for app, if I define app like this. Note that Scala compiler will not compile if I put wrong kinds. So for example, if I put app with two type parameters, but a and b, but a is not a type constructor. So the kind of a must be the function kind, or the type function kind. If this is not so, the Scala compiler will give an error. Let's look at the test code. So here I define a type function, just any type function. Here I define the app as in the slide. Now, if I define type x like this, I'm applying the type function app to the arguments g and int. G is itself a type function defined here, and so that's okay because app has the right kinds of arguments here. So after I apply this, x becomes the result of applying g to int, which is this. Let's verify that x indeed is this. So let's say x of type x is left of that, and that compiles. Now, if I were to try writing code like this, it won't type check, because the kinds are wrong. The first argument of app must be a type function, but it is not. It is a basic type. Similarly here, the second argument of app must be a basic type, but it is not. It is a type function. So neither of these two will type check. Let's look at a little more complicated example. We will write the kind notation explicitly here. Again, first we define a type constructor. Then we define app, which has two arguments, and the kind of app is this. And we can write more verbosely with argument names if we wish. So f has the kind star to star, a has the kind star. So actually Scala requires the syntax that shows the kind. You cannot just say f comma a. If you write app of f comma a, it will assume that f has the star kind. So you have to write the syntax if you want a higher kind, higher order type. Now, let me just say, the terminology in functional programming has this higher kinded types. I don't think it's very illuminating. Types are types, they're not kinded. We don't say it's a higher typed function. We say higher order function, because it's a function that takes functions as arguments. Here we have functions of types that take other functions of types as arguments. Why should we call it anything else than higher order type function or higher order type? Higher kinded is not very illuminating here. So here's another definition where I define app with two p's, which is three-parameter function. The first parameter is itself a higher order type function of the same kind as app. So I can express it like this in Scala. It's a little harder to read. I have two arguments. The first argument is a type constructor. The second argument is a basic type. And the function p is a type function of these two arguments. So the kind of p is this. The kind of q is this, and the kind of r is this, basic type. So then I can define this. You see, I'm applying, when I define the type function, I say I need to apply p to q and r, and so q is of the right kind to be put into p. So now I can say define x, the same x that I had here defined like this, app by gint. I can say app of app gint. It will be exactly the same thing. I verify the same things as I verified before, namely that putting arguments of wrong kinds does not work. Now, there's one other thing that we would have to do if we want to be completely free dealing with type functions. Remember that in functional programming, it's important to have anonymous functions, not just named functions. Anonymous functions enable a lot of freedom in programming, and without them, things are difficult. So functional programming really wouldn't work well without anonymous functions. Quite similarly, we need anonymous type functions. Until now, all we've seen were named typed functions, so all these names. But we want also anonymous type functions, because without them, things are just not always possible to express. Anonymous type functions are more difficult to write in Scala, but it is possible to write them. And there is a compiler plugin that makes the syntax easier. It's just a syntax plugin, and I use that plugin, which is available at this address. It's called the Kind Projector plugin. So let me show you how it works. I define a type function, just a simple one. Then I define the app, just as before. Now, I want to define a type function, a higher order type function, that takes a type constructor and applies it twice to its type argument. So app2 should take a P and a Q, and then it will put Q twice into P, so to speak. So you see, the first argument of P is a type constructor. Now, previously I put Q as the first argument, but now I want to put Q twice. I want to say Q of a type argument. To express this, I need an anonymous type function, because I want to put that anonymous type function as the first argument of the type function P. Unless I have that, I cannot express this behavior. This is the syntax of the kind projector. It has this special symbol lambda, and then it allows me to write my anonymous type function like this, where x is now a new type variable, anonymous functions type variable. So this is a very similar syntax, except under lambda, and that is what the kind projector provides. Now, instead of lambda, I can write, instead of the Greek letter lambda, I can write lambda in Latin alphabet like that, which is just more verbose, no difference. So this app2 has this kind. It's the same kind as app from the previous example, except that here it, instead of using Q once, it uses Q twice. It composes Q with itself. Q is a type function. It composes that type function with itself. In order to express such behavior, we need anonymous type functions. So now, if I apply this app2 using the O2 type constructor, which is just an option of a tuple, AA, then this option of a tuple will be applied to itself twice. So it will become option of a tuple of option of tuple, option of tuple. And indeed, that's what it is. X2 has this type and it type checks. So this is a bit of an advanced topic, the anonymous type functions, but this is similar to anonymous functions. So just the syntax has to be a little different. So as a result of this, we have a uniform view of values and types. Types are to values, as kinds are to types. Type classes are just a certain sort of kind. Function kind, type function is another sort of kind. So there are different kinds. There's type function kinds and type class kinds. And you can combine them. You can have a type class for type functions, which is, for instance, for the functor. Functor is a type function, and we can have a type class for it. You can, of course, have type classes for higher order types as well. So the syntax becomes a bit more involved, but you can still do it if there's a use case for it. So I showed you that there are some use cases for all these generic functions. The main idea being that you want to save your code, you want to implement things generically, write code once and have it work for all functors, for all types from a certain type class. And another thing that Scala provides by way of convenience is the implicit method syntax. So let me show you what that is. This is very often used together with type classes, but this is a purely syntactic convenience. There's no more power that this brings us. The partial type to value functions are exactly the same as before. All of these implicit things are just syntactic conveniences that make code shorter. The basic idea of partial type to value functions remains the same. So here is how it works. In Scala, in principle, there are two sorts of syntax available for functions. The first is the syntax similar to that of the ordinary mathematics, where you say function name, in parentheses you list the arguments. Scala also allows you several lists or one or more lists of arguments. Another way is to have a syntax like this, x.func of y, which is a method kind of syntax, like object-oriented method. All pretty much object-oriented languages use this syntax. In Scala, there is another equivalent syntax. Whenever you can say x.func of y, you can also say x space func space y. Sometimes that's easier to read. Now, these functions are similar, but they're just implemented differently. And in some cases, you might prefer one, and in another case, another. So here's an example when it is convenient to have the method-like syntax. Imagine we define a function called +++. It is a partial type-to-value function, and the type domain for it is this type class has +++. And then there are some arguments, and one argument is of type t. So you would have to call this function like this, +++ of t and arg. Now, you would like to write this instead. This is much more readable. T +++ arg. Whatever +++ means in your application, this is certainly easier to read than this. Scala provides a way of implementing that syntax. And this is what I call the implicit method syntax, or extension syntax. So what is the implicit method syntax? Suppose you want to convert func, which is a partial type-to-value function, to this syntax. You declare that as a method on a new trait or class. Well, a new trait is necessary. Usually a class is sufficient. And you declare an implicit conversion function from t to this new class. And this implicit conversion function is a PTVF using the same type class. So in this way, you automatically extend your existing type class with new syntax. You do not change the type domain of your type class when you do this. Since you don't change the domain, you don't need to change the code of the existing type class. So this can be done in a different piece of code or different library, different module. And the implicit conversion function can be done as an implicit class. I will show you the code in a second. And that makes code shorter, actually. Here's how it works. Suppose we implement the Monoid type class. So this is our partial type-to-type function, which has some methods in the trait. Here is our syntax. So this is this new trait or class that we need to implement for the syntax purposes. I call it an implicit class, and it has one argument, which is, so its implicit class is really a function that at the same time defines a new type of this name and the function that creates values of this type. And the function has this argument. It also has an implicit argument of the partial type-to-type function, which means that this is a partial type-to-value function. So like I said, implicit class means you define at once a new type and a function that creates a value of this type with this argument. So in this way, it's doing what I said here to do in one step. I define a new trait or class, a new type, and I define a function that creates values of that type from values of type T. So here's type M. At the same time, I constrain the type parameter M to belong to the type class Monoid. So now it's a very short code comparatively. All I need to do now is to implement a method that I want. The method I want is the syntax method. So let's call it append log. I can change the name if I want, because this is an extension. So I do not actually change the functionality of Monoid as it was previously defined. I'm adding new syntax to the previous syntax. The previous syntax will still keep working, and so I can have a new name if I wish for the new syntax. So this is the method that will be available on Monoid types. And the method will be append log with an argument y. I will just use the combine method from the Monoid. And there's no new functionality here. I'm just repackaging the combine in a new syntax. So how does this work then? Here's a data type in my application, which is log data. As I mentioned before, logging is a typical Monoid example because there's an empty log and there's appending to a log. So you can put two logs together and it's a bigger log again. So let's define what empty log means. It's a string that says no logs so far. And then let's create a Monoid instance, which is a Monoid of type myLogData. I'm using implicit val here, why not? So the combine function will check if one of the logs is empty, then I just take the other one. If not empty, I will concatenate logs and add a new line between those log lines. So this is a little more sophisticated than just concatenating strings. So my logs will be well formatted, will always be new lines separated. Then I import this Monoid syntax. Now this is the new thing that I defined here for syntax. I import. And now here's the code of my application. I have some log values here. One log message, another log message. And then I just say initial log, append log, log data 1, append log, log data 2. So I'm appending all these logs. So this is the new syntax that I have just defined, and it works. The log result is equal to this string. What I could do, for instance, very easily now, is I could rename this append log to plus plus plus. What happens then? I have code like this. So this might be more readable. Depending on my application, I'm free to add new syntax without changing the type class that was defined before. So I'm completely open to extension without having to change any of the library code for Monoid. Okay, so to summarize, what we have gained is that the partial function that we define appears as a method on values of the relevant types and only on those types. So the plus 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 will be only defined on those types that have a monoid instance in my previous example. And the new syntax is defined automatically on all the types. I did not have to define plus 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 specifically for my log data. Not like that at all. I define it generally for any type M that has a monoid instance. So this is the power of type classes. Let's now go through some worked examples. This is going over the entire material of this tutorial. The first example is that we want to define a partial type value function of this kind. The bit size has a type parameter t, and if that's an int type, it returns 32. And if it's a long, it returns 64. Otherwise, this type to value function remains undefined. How would we implement that? We go systematically. So a partial type to value function requires, first of all, a partial type to type function to define the type domain. So let us define this type constructor as a case class. We could not just use a type definition because that's all going to be int for all the types t, and so that's going to be a type collision. So let's do a case class instead. So this is a type constructor that will be our partial type to type function. Now we want to define this only for int and long. So we do implicit val, bit-sized int, evidence is bit-sized with value 34, and long evidence has bit-sized with value 64, 32, 64. Notice we put into the type that will be our type function, we put the information that this function needs. The function we want is the bit size that will return 32 or 64. This information is carried by this type. So the type evidence value carries the information we need. That's almost always going to be the case for any partial type functions. The partial type to type function represents a type that carries all the information we need about the type that the type to value functions will use later. And the only information we're required to return is this number. So let's put this number as our type in here. Now we define the partial type to value function. So bit size has an implicit argument of type bit size t, and it returns just this evidence value.size. That's enough. That's all we need to do. And indeed, this works as expected. The test verifies that. The next example is to define the monoid instance for this type. Now notice this is an option of a function from string to string. So I'm going to use that as a type. And I'm going to use the cats library for the standard monoid type class. So my tests here are all going to use the law checking for the cats library that I implemented in a different file. So this is my data type. I just define this as an option from string to string. Since this is such a simple type, no need to do case classes here myself. So defining a type class instance for the standard type class in a library means that the type constructor, the PTTF, is already defined in the library. It is the monoid, already defined in the cats library. The type constructor is there, but I'm going to add more types to the domain. So that's always going to be possible, adding more types to the domain of this partial function. And this is so because the monoid is not a sealed trait, it's just a trait, not sealed here. And so I can always add new instances or new types to the type domain of that partial function. So I'm going to add this type to the type domain. In order to do this, all I need to do is to create some value of the type monoid of data. That's all that is required. Now, so here's one value I create of this type. I need to override two functions, empty and combine. The empty is a value of this type. And combine is a function from two values of this type to a third value of this type. So what is a naturally selected value of this type? Well, I can think of many. One could be, it's an option of identity function, so, or some identity function. So that's what I write here. And the combine would have to be such that if there is a non-empty option, then I compose these two functions. So I have sum of one function, string to string, sum of another function. I compose these two functions. So this is the code I'm writing here. So if there's a sum and a sum, then I compose these two functions. In all other cases, I return none. So clearly, the identity function here is a neutral element for this operation. So if I compose identity with anything, I get the same function again. In all other cases, I get none anyway. So this will satisfy the laws, hopefully. It's kind of a little boring instance because it very often produces none. Whenever one of the two parts of the combine, one of the two arguments of the combine function is a none, it will produce none. Another instance would produce none much less frequently. How would that work? Well, if one of the two arguments of the combine function is none, then I return the other one. And so none becomes the neutral element. And then I do compose the functions if I have two functions. So basically I prefer to keep the function if I have one, the non-empty option. I prefer to keep it. Unless both are empty, then the result won't be none. So that's perhaps a more interesting instance. But we're free to choose one or the other. It's not really clear at this point which one would be more interesting. So there could be different implementations of the same type class, and there could be use cases for both of them. Because of this, I don't make them implicit in my test code. I want to keep them explicit. Implicit would be possible with only one of them, because I cannot have two implicit values of the same type. And I check that both of these satisfy the monoid laws. Now, the satisfying monoid laws requires two implicit arguments of the arbitrary data and monoid instance. So since I'm not doing the implicit, I have to put these arguments by hand. And if I look at this function, it has an arbitrary type class and a monoid type class. So I need two implicit arguments. And the arbitrary data, I don't know where to get that, but it's implicitly available. So I just say implicitly arbitrary data, and that's how it works. Both are valid monoid instances, it turns out. The third example is by assuming that A and B are types with monoid instance, I define a monoid instance for the product type. So this is an interesting example because it shows that I don't have to implement everything from scratch. If there are monoid instances for some previous types, I can just define monoid instance for a new type and don't have to write a lot of code. Maybe those monoid instances for the previous types had a lot of code in them, but this code is not very large. So how do I do that? Well, I use this implicit def mechanism, which is I define a function that produces the type evidence for the product type. So the type evidence is the value of a type monoid of product type. So I produce this type evidence given the type evidence for monoid A and monoid B. So this is what it means to define monoid instance for product AB if I have monoid instances for A and B. It means to make a function that takes the two monoid instances. I remind you that monoid instance is exactly the same as a type evidence value. It's just for monoid. So type class instance is exactly the same as a type evidence value. So it's a value of the type that is the partial type-to-type function applied to the type that we're producing evidence for. So if we want producing evidence for type A, then type evidence is something of type monoid A, and that something will typically carry the entire information we need to implement the monoid for type A, so that is also called, for that reason, the monoid instance for type A. And so our task is to implement a function that takes monoid instances for types A and B and produces a monoid instance for type product AB. Well, so how do we do that? We just say, well, new monoid, which is the way to extend the trait very quickly. And we override two methods. So we need to produce a value of type tuple AB, and the evidence will give us a value of type A and the value of type B. So we just put them into a tuple. And the combine works in a similar way. So we know how to combine two A's and we know how to combine two B's. So that shows us how to combine a tuple AB and another tuple AB. We just combine A's separately and we combine B's separately. And we use the evidence values to fetch the combined functions from the one monoid and another monoid. So that's all. Let's test. So this test is just going very slowly to make it clear exactly what we're having achieved, what we have achieved. So first, we have no int or double monoid instances in scope. Just make sure we don't have them. So this would not compile and this would not compile. Now we declare these instances. So for int, let's say the empty value is 1 and combine is product. That's fine, that works. And for double, empty is 0 and combine is a sum. That works too. Multiplication actually wouldn't work because it's not precise enough, and it would violate associativity by precision errors or by round-off errors. So I use addition, not multiplication, for double. All right, so after I have defined instances as implicit values of these types, we have both int and double monoid instances in scope, and this will compile and work. Whereas here it did not. Alright, so now that should be sufficient for us to be able to derive the monoid instance for the tuple int double automatically. And that works. So the monoid laws work. So that's this test runs, and that's how it works. The next example is to show that if A is a monoid and B is a semigroup, then the disjunction A plus B is a monoid. Now to show this means, again, to write a function that takes a type evidence for monoid of A and a type evidence for semigroup of B, and produces the type evidence of monoid of A plus B, or using equivalent terminology, type class instance for monoid of A, type class instance for B as a semigroup. These are two values. These are going to be arguments of my function, and the result of my function must be the type class instance for monoid for type A plus B, which is either AB. So showing this is not some kind of theoretical mathematical exercise, but it's a specific coding exercise. I need to write a function that produces the evidence of monoid type class given these two evidences, and I want to check laws. So here's how it works. This is this function. It has two type parameters and two implicit arguments. One is the evidence that A is a monoid, and the other is the evidence that B is a semigroup. Remind you that semigroup doesn't have the selected element. Monoid has both a selected element and the binary operation. A semigroup just has the binary operation, no selected element. So it's interesting that if we combine the two of them with the disjunction, then the result can be a monoid. While in the previous example we had a product, both of them needed to be a monoid for the product to be a monoid, because we need to produce the empty value, so both of them must have an empty value. But here, with disjunction, we don't need to produce both empty values. Just one is sufficient. So that's why one being a monoid and another is a semigroup is sufficient. Alright, so let's see how that works. So empty element needs to be of type either AB. Well, obviously, we don't have a naturally selected element of B, because it's a semigroup. We do have a naturally selected element of monoid, so we produce that. Okay, now how does combine work? Well, it takes an x of either AB, y of either AB, and needs to produce again an either AB. So we have different situations. We can have A and A. We can combine A and A, obviously, because it's a monoid. B and B, we can also combine B and B, obviously, so these cases are easy. And now there are two cases when it's not clear what to do. Now we have a left of XA and the right of YB, so how do we combine? Now we can't really combine A and B. We have no idea what these types are, except that one is a semigroup and another is a monoid, but they're not combinable directly, one with the other. So we have to ignore one of them. Which one? Well, we can think about this, but basically things don't work unless here you ignore the x and here you ignore the y. And let's check that this is correct. First, we don't have instances, then we define instances for int. So let's see. We need something that's not a monoid, that's a semigroup. It's kind of hard to come up with such a thing. Most operations we know are monoidal, like plus has a neutral element. We need an operation that does not have a neutral element, but is associative, so it's not easy. Well, fortunately there is a paper, which I'm referring to here, that describes a function that is non-commutative but associative, and this function does not have an inverse, and it does not have a neutral element. So I'm using this function, which is Budden's function, which is described in this article, defined by this formula. Very simple formula. It's kind of curious that this function is not commutative and yet associative. In any case, this is fine for a semigroup. And for the double, I use the same instance as before, the addition with 0. And it works. So if you change this to x instead of y, or here to y instead of x, it will not work. It will break. So this is a curious definition, but that's interesting. We have only one choice to define a monoid instance on a disjunction. So think about it. Option is a disjunction. So if you have a monoid, then option A is a monoid, and option of A is also a monoid. Disjunction of two monoids is a monoid, because a semigroup is less than a monoid, so that's good. Conjunction of two monoids is a monoid. So you can combine monoids quite easily. And this is a generic way of defining these combinations. The next example is to define a functor instance for this type. Now here we're using try, which is a Scala standard library API, which is not a data type, it's a special thing defined in the Scala library. Sequence is another thing defined in the Scala library. So we're just trying to say, how can we do things with Scala library defined type constructors? Can we make them into functors in terms of GADTs library, let's say? Yes, so we say, here's this type. I use the type definition to define the type function f. So that f after this becomes a type function defined like this. And then in order to define a functor instance, I need to define an implicit value of type functor of f. So that's why first I define this name f like this as a type function, and then I declare the new functor instance by overriding the map, and then I just implement the map. So how do I implement the map? Well, fa is this f of a, which is a sequence of try of a. I can map over a sequence. The result will be a try. I can map over a try, and the result will be again a try. So this is a functor because it has a map. This is also a functor because it has a map. Composition of two functors is a functors. If it is a functor because I can just compose maps like this. And all I'm doing here is to make the GADTs library aware of this being a functor. So that's all I need to do. I'm not going to check laws here because it's quite a lot of work to produce arbitrary values of these types, especially the trie. But it is easy to verify that composition of two functors is a functor. So we could have checked the laws if we wanted to. The next example is to define a CADTs bifunctor instance for this type function. And notice that this type function has two type parameters, x and y. And bifunctor is a type class defined in CADTs as a standard type class that is like functor except with two type parameters. It's a functor with respect to both of them. So to define that, first we define a type function or type constructor. The name of that is Q, as we are given here. And then I'm using either just to reduce typing. I don't want to declare my own sealed trait and the two cases for the disjunction. But I could, of course, declare Q as a sealed trait with two type parameters. It would be just more typing. Then all I need to do is to define an implicit value of type bifunctor of Q. So this is a code that does that. To do that, I need to override this function, bimap. So bimap means that it's a functor when you transform both type parameters at the same time. Then it's a functor. So bifunctor means that it's a functor with respect to both type parameters at once. So you transform both of them at the same time, and the result transforms as you would expect. So for instance, either of AAB transformed with two functions, two arbitrary functions, one a to c and the other b to d, replaces this with either CCD. So that's what is required. Now, I'm not going to write code for this function. I'm just going to use my Curry-Howard library to implement the code automatically using the type. This is possible and it works. I'm just trying to reduce the time I'm spending writing code. Now this is something we already know, how to implement functions given their types. And this work can be done by the computer, so why not? The non-trivial part here is how to define type class instances, and that's what we do by hand. Having done this, we have defined this implicit value, and we check the bifunctor laws. Now, the checking the bifunctor laws is again a function I implemented in my test code. The next example is to define a contrafunctor type class. So this type class is like functor, except it has contra fmap, where the direction of the arrow is counter to the direction of the transformation of the functor values, the type constructor values. So it's a contrafunctor, and the example consists of first defining a new type class, having this partial type to value function, and then to define an instance of this type class for the type constructor of this formula, which is type argument a going to integer. So this is a contrafunctor because the type argument is to the left of the function arrow. And we expect to be able to define an instance of a contrafunctor type class for this type constructor. So let's see how that works. So the given contrafunctor is this, and let me define the type right away. So after this, I have defined the type function C. So first we need to define a new type class, which consists of a partial type-to-type function carrying the data that we're required to carry. This type function is contrafunctor with type variable, which is the C. Now C here is a parameter name. It's a little confusing perhaps. Let's call this CO, just so that we don't confuse this with this C over here. So this is the contrafunctor. This is a trait having a def method of the signature we're required to have. And in order to show that this type domain includes this C, we are required to produce a value of type contrafunctor of C. So we do it like this. So we can either do a new contrafunctor, or we can do an implicit object extends contrafunctor. Is the same thing. We could do that. It would be equivalent. We need to override this function, and this function needs to have this type from f b to a to int to b to int. Again, I let my Curie-Howard library handle this code. And once I'm done, it will work. Let's do the same thing with Cat's library. Cat's library has a contrafunctor type class, which is called contravariant. And it has a different name and a different type of the function. Instead of fmap, it has map, so not a flipped argument order. Other than that, it's very similar. So how do I know this? Well, let me show you how I know this. I just do that. It's not happy because I need to define contramap, as it tells me. So I press this button here and I say implement methods. It tells me what methods I need to implement. Now C of A is A to int, as far as I remember. And now I can just say implement here. And that's my Curie-Howard library at work. All right, now let me do the type annotation. Which is required, and then I'm done. And then I define equality comparison function for this C. It's a function, so C of int, let's say, is a function, and comparing two functions is not immediate. You need to substitute different arguments and compare results. So that's this C equal code that says for all t, the C1 of t must be equal to C2 of t, and then the function C1 is equal to C2. So that I substitute into the law checker, and it will check my laws, and that works. Tests pass here. The next example is to define a functor instance for the recursive type defined by this formula. So here, let me first define this recursive type. So it's a sealed trait with 3 cases, and the third case is recursive. It contains the same type of the trait itself. All the cases of the trait are parameterized by the type parameter a and extend q of a. So this is a functor because a always occurs to the right of the arrow or here, but this is the recursive instance, so that's fine too. So let's implement the functor instance. We say new functor, so functor is the cat's functor. Just to check. It needs to override the map. Let me type override here. It's not necessary to type override, but it's more checking this way. If I mix up the types, it will tell me that I'm not overriding it in the right way. So with these object-oriented things, the more checking you have, the better. So type override, make sure that it checks that you're overriding it with the correct type. Okay, so what does this function do? This function takes an fa of type q of a. It takes a function f from a to b, and it needs to produce q of b. So to do that, we have to match on this q of a. Let me rename this to qa for clarity. The first case is the function from int to a. Well, obviously I need to compose this with a function f, and then I will have a function from int to b as required. The second case doesn't have any a's, so it remains unchanged. Just the type parameter is changed. There was c2 of a, now it's c2 of b. Okay, so this is option int. Why is it option int? I'm not sure. Something is fishy here. Well, x is int, that's true. Oh, I see. It's the case, it does not tell me the type. It tells me something else. It tells me the possible parameter types. So, never mind. The interesting case is the third case. So, the q here is a q of a, and I need to produce q of b. Now, I don't know how to produce q of b, so I use the recursive call to the same map that I'm defining, and I call this on q and on f and put this into C3. So in this case, I remain in the C3 case, and I transform this q by using the recursive definition of the same map. So that's how I have to do it. There's no other way, really. So in this way, we define the functor instance. So let's see how I would check that this functor works correctly. So for example, I get this implicitly functor q.map is the value that I just defined. I could have said q functor instance.map because I just defined it here, but I don't want to know about these names. These names are completely unimportant as long as you make them implicit. So I'm going to use this as my data and put identity function on it and see if that transforms the data into the same form, and it does. So that's just a sanity check. I'm going to check the laws more systematically in a second. To do that, I need an equality comparison. So that's a bit involved because there are many cases. So I need to compare each case, and then there's a recursive case as well. And I need to compare functions. So all of that requires extra code. So here's the case for comparing functions. Here's the recursive call. So if I need to compare C3 with C3, I recursively compare the contents of C3 using the same C equal function. So that's how this works. This is just to see that this works. This would fail if they're not the same. And finally, I call the functor law checker on this type using C equal, and the tests pass. The final worked example is a bit more advanced, so I started, but it's not so bad. It's to show that you can define a functor instance for a disjunction if you have functor instances for the two type constructors. So this is a bit more advanced because you need to define a type function that is a disjunction of two given type functions. So I need to define an implicit def, which would have two type arguments, f and g, each of them being type functions, and two implicit arguments, which are the evidence that f is a functor and that the g is a functor. But what am I going to return? I'm going to return evidence that f plus g is a functor. But what is f plus g? F plus g is a new type constructor. In other words, a new type function. But it doesn't have a name yet. And I cannot have a name for it because f and g are my parameters. So the only way for me to express this is to say that this is an anonymous type function. So I'm returning type evidence that an anonymous type function is of type class functor. And this is this anonymous type function. It's x going to either f of x and g of x. So that's a type. X is a type parameter. And this is a type expression that defines my type function. And so the lambda syntax is a syntax for anonymous type functions using the kind projector plugin. So that is the kind of difficult part. And other than that, this code is quite straightforward. The difficult part is reasoning about these higher order type functions. So for convenience, I can put a name on it in the body of this function, but I cannot put a name on it before I define the function return type. So that's why this kind projector is important. But other than that, it's not so bad. So type, either fg, is a type function that is the same as this anonymous type function over there. It just has a name now, and that's now easier to use. I can just put this name whenever I need it. So now I return this functor instance by overriding the map. I have an either fg of a, and I have a function from a to b, and I need to return either fg of b. So how do I do that? Well, I get this fga, which is either f of t or f of a or g of a. I match in it. If it's f of a, then I use the evidence for f to get the map of f of a with the transformation t. And if it's in the right, I use the evidence for g to get the map for the functor g. Use that map on the g value and the transformation t. So that's it. That's a very straightforward code. Now I test this code. I create functor instances for some simple data types, D1 and D2, very simple data types. And for these data types, I can just implement functor instances like that automatically. And finally, I say, well, let's call this D1 or D2. So I, again, for convenience, introduce a specific name for the disjunction of two functors. So this D1 or D2 is now a new type function, which is a disjunction of the two type functions D1 and D2. And I check the functor laws for D1 or D2. Now, the implicit function here was called invisibly. I didn't have to call it myself to produce the type evidence that this is a functor. But you see, this function requires that evidence. It wouldn't be even compiling if I didn't have that evidence. Since it compiles, then it's correct. Now, in this code, I will show you how I attempted to do this without the kind projector. It's kind of difficult. And the problem is, we need to define this name. If we cannot have anonymous functions, anonymous type functions, we have to define this name somewhere, but we cannot define it before we have the type constructors f and g. And so we have to define it inside the body of the function, and then we can define the instance like this and check the laws, but nobody outside of this function can see that instance. Because this is a function, this is not an object, this is not a val, this is a function, it has to be called, and when you call this, it will define the instance and check the laws for it, which works. But nobody outside of this code will be able to use this instance. So if you don't use the kind projector, then you can't really express this situation that you actually have defined a functor instance for a disjunction of two arbitrary functors given as type parameters. And this functor instance, you see, it's usable outside of this code. So I can put this into a library, I can put this into the companion object of functor, and nobody will have to do any imports or anything, it will just work automatically. So that's the power of implicit function definitions that can automatically build new implicit evidence value. So this becomes a new implicit evidence value that is automatically built up from existing implicit evidence values, these two. So this concludes the worked examples, and here are some exercises for you that are quite similar to the worked examples. And once you go through these exercises, you will really have a solid understanding of type functions and type classes. By way of conclusion, let me summarize what are the problems we can solve now. We can define arbitrary partial type-to-type functions and partial type-to-value functions. Type classes are just a way to systematically manage partial type-to-value functions. They're not different, they're just PTVFs, understood in a somewhat more systematic way. We can define these together or separately. We can define some of them, then later more partial type-to-value functions. We can combine them. We can use a CADTs library to define instances for some standard type classes such as Monoid, Semigroup, Functor, and so on. We can derive type class instances automatically from previously derived ones or previously programmed ones. And we can reason about higher order type functions, types, and kinds whenever that is necessary. So what is it that we cannot do at this point? Well, there's still things we cannot do. One of these things is to derive type class instances automatically for polynomial data types. That is, the case classes sealed traits with disjunctions and case classes with data in them. Although the Curry-Howard library can do this in some cases, it cannot do this in all cases, and we cannot do this automatically by implicit defs either. This requires more advanced tools, which are available in the Shapeless library, and I have a link to a book, online book, a guide to Shapeless, where it is explained in depth how automatic derivation of type class instances works in the Shapeless library. Another thing we cannot do is to derive a recursive type generically from an arbitrary type function. So we have just seen an example of defining a functor instance for a recursive type, but this type was defined by hand. So suppose we have a type function f given as a parameter, and we want to define a recursive type r via this equation. This is a recursive type equation, or also called a fixed point equation. R is a fixed point of the function f. So this fixed point is a function of f, and that function is usually denoted by y, the so-called y combinator. It takes an f, which is itself a function, and it returns its fixed point. So the y must be defined by a type equation of this sort. So y of f must be equal to, y of f is that r, which is equal to f of r. So y of f must be equal to f of y of f. But this doesn't compile. Scala doesn't allow us to make things like this. More work is necessary to even define such things or have a generic type function that computes the recursive type. And we haven't seen how to do it. Also, for such recursive types, we cannot derive type class instances automatically. So for instance, if f were a functor with some other type parameter, then r would also be a functor. Or if f is a monoid, then r would also be a monoid, or something like this. We would like to derive automatically type class instances whenever they exist, and we cannot do this with the tools we have seen here. Now, there are some advanced libraries like Matryoshka that implement type-level recursion or type-level fixed points that are able to handle these problems. I'm giving you a link here. Also, Shapeless might help, I'm not sure. In any case, these are more advanced topics, which are perhaps further away from practical applications than I would like. And there are some interesting discussions. There's a blog post, very interesting series of explanations of this kind of stuff that I encourage you to look at if you're interested. This concludes Chapter 5.